Welcome, everyone, to another EECS Colloquium. Our speaker for this week is Srini Devadas, who was actually a student here in our department and then
a long time ago.
Oh, but now he's back. So Srini works across many different areas that span kind of the intersection of EE and CS. That includes CAD and security and also computer architecture. He's a fellow of IEEE and the ACM, and he's also won the 2 highest teaching awards at MIT for his teaching. And he's going to tell us today about traveling, time traveling in hardware and software systems.
Thanks, Bjorn. It's a real pleasure to be here. I left here 28 years ago, so it's been a while. And when I came back, it was a pleasant surprise to see how many of my professors were still here, and some of the grad students that I was with had become professors. And I'm happy to report that none of the students that I was with are still students. So, so that's good, right? I mean, for all I know, right? I haven't checked fully, but. Speaking of students, this work was largely done by my PhD student, Shangyao Yu, who did the work, made the slides, and I get to imitate him for about 50 minutes. So it's work that corresponds to work in computer systems. I'm going to talk to you about computer architecture and database systems. Every computer architecture talk has to have some mention of Moore's law. So here it is. We've written Moore's law, which is a printing press for the currency of performance. This is Samar Namarasinghe's term, not mine, but I like it a lot. And it's allowed us to build software systems that really were unimaginable a few years ago. Of course, things are somewhat problematic, simply because while Moore's law has been going on for a while, if you look at the transistors up there, they've increased every generation or doubled every generation. Back in 2005, Dennard scaling stopped. So that essentially meant that the clock frequency of processors that you could buy from Intel stopped at around 3 gigahertz or so. And then essentially what happened was you had a situation where, because clock frequency stopped increasing, you had to increase the number of cores. You had to increase parallelism on the chip in order to use the transistors. Right? So parallelism became more important. And as Moore's law grinds to a halt, we're going to have to use parallelism at many different levels of abstraction, not just at the transistor level or the functional unit level, but putting multiple nodes, sockets, data centers together to really keep performance up and to increasing levels of to keep the performance levels increasing. So I want to talk to you a little bit as context about the different kinds of parallelism that are out there, and there's some impact of the work that we're doing on these different levels. So at the instruction level, you think about registers, and you think about perhaps running these first 2 instructions up there in parallel, but the last instruction uses the result of the second one, the D variable, so that has to be run in series, so that's instruction level parallelism. At the transaction level, when you have databases, the way you think about this is simply that you have atomic transactions, so the transactions themselves have to be executed in an atomic fashion, even though they have multiple operations in them, but they can be kind of moved around in any which way. So you could take these 3 transactions and execute them in any which order, and it's fine. But once you execute this transaction or start executing a transaction, you can't have another one step on it. Right? So that's a different kind of parallelism. There's the thread level parallelism, a classic example of this, and there's many better ones probably, but an easy one is simply doing matrix multiply and perhaps having a different thread computing each entry of the product matrix, and you have to worry about synchronization in this case. These threads may be running on different cores. They could potentially be running on different sockets as well. At the task level, when you go do a search on Google or your favorite search engine, there's a lot going on in the background associated with the particular functionality, be it MapReduce or whatever it is running in the background, to compute what you want as an output. And of course, there's many users doing this, and so that's user-level parallelism, where you have many queries to the same data center. And you think of this as another name for this is embarrassing parallelism. There's really a lot of parallelism out there in this context. So all of this is going to become more important in my view, and it's nice to be able to have advances that are hopefully fundamental in nature that will allow us to exploit these different kinds of parallelism. And hopefully by the end of this talk, you'll get a sense of whether we're doing interesting work in this area or not, and hopefully you'll be excited as I am about this work. Dependency destroys parallelism. An example here is something that compiler folks gnash their teeth over. You have a situation where clearly there's a dependence across iterations of the loop, and it's kind of an annoying kind of dependence because it's indirect addressing of these arrays, and so you can't do fancy tricks like putting pre-computing, because B of I is this sort of random array that is going to produce a random value in effect because you don't have control over B of I, and it's kind of hard to deal with. Right? So dependency destroys parallelism. This is one example of that. And you have to compute these iterations in series. Now, there's different kinds of dependencies. And so this is really coming to the core of our work, where we think of dependencies at the memory address level as opposed to the computational level. And there's 4 kinds. And you can imagine what those are. You have reads, and so these 2 reads are happening in different threads. And so they're staggered in that fashion, as you can see here. And there's no real dependency because you're not writing the variable, so you go ahead and read it in whatever order. When you have 2 writes, it's a little bit more confusing because most writes are actually reads of a variable followed by a write. But in the pure sense, if you have 2 writes, it's really a function of your semantics of the program as to whether you want to have a dependency between these 2 writes or not. Right? And maybe you don't care because you don't care as long as these 2 writes happen atomically. You don't particularly care as to which order this happened. Right? But that's really a function of the program semantics. And it's a function of the level of parallelism that you're looking at, instruction level or the transactional level. The classic dependency that you saw an example of at the instruction level is the raw dependency, which is read after write. Here, it is very clear. I need this value that was just computed. Okay? And there's no 2 things about it. I mean, if I get a stale value and I go run off and compute the matrix product, there's a problem here, right? So that's a clear dependency. And it's been nice to avoid this. We don't do a whole lot with this dependency, the raw dependency. But what we're going to do is we're going to use flexibility in the definition of correctness of our program to virtually eliminate what are called war dependencies, which are write after read dependencies. Okay? And I'm going to give you a sense of how this is going to happen, why we have this flexibility in the next minute or so, and then we'll dive into specific examples of using this flexibility, exploiting this flexibility. So we talk about dependency, and dependency is across time. But what's time, right? There's different definitions of time. I mean, the easy one is physical time. I'm out here, talking in sequence, slides coming up in physical time. But you could also have Lamport clocks, logical timestamps that are assigned to instructions that say that, I've just taken an arbitrary order here with, Beyond being first and Carlo being second and me being third, or the other way around, with me going first, etc. And it may be that that I finish my task much later than Carlo or Beyond, but I'm front of the line. I'm the front of the line. Logically, it was my timestamp that came first, and that's obviously going to reflect on the correctness and the semantics of the program execution. But there's no reason why logical time has to be the same as physical time, and there's no reason why time can't be a combination of logical time and physical time, right? So you don't have to have one notion. You can mix the 2. Ultimately, time is the definition of ordering, right? In a local setting, when you have people in this room or in a processor, clock cycles give you the effectively physical time because a clock cycle follows another one, right? But if you have EST, over in New England, and PDT out here, or EDT in New England and PDT out here. Not quite clear what the notion of time is. And when you interact and when you have skew, you have to use logical time in many cases to resolve this type of conflict, right? So time is really a definition of ordering, and you can define the ordering based on a combination of physical time and logical time. So let me give you a simple example of how these could be different, and how this would affect the war dependence, the write after read dependence that I just talked about. So what I have here is the initial variable value of the variable A is 10. I have thread 0 that wants to read A, and thread 1 that needs to write A. And we have a war dependency here. So what we'd like to have happen is that the read should get the old value, and the write should create a new value. All right, that's it. I mean, seems perfectly reasonable, right? Well, there's nothing that says that the write can't happen physically before the read, right? Because I could go ahead and take my value. I may not commit it. I may have a local value. I go ahead and do the write. In fact, I'm even committed into the global repository and set A equals 13. But the fact is that the read operates on a local copy, which is A equals 10, and that happens much later, right? So logically, the read was earlier than the write, but physically, the read was after the write, right? So simple example. And so there's absolutely no reason why we have to be committed to physical time, right? That's essentially what I said here. And so then it comes down to, OK, that's fine. I mean, that makes sense. It seems like it did the correct thing. But what is the definition of correctness? When we have a parallel program, it's non-trivial to talk about what the outputs of the program should be and whether they're correct or not, because there are many interleavings of different threads running in different time zones, with different notions of time. So we have to have a definition of correctness. And obviously, there's been definitions proposed here. And we're not going to change the definition of correctness. We are going to essentially say something with regard to parallel program correctness based on the classic notion of sequential consistency. And sequential consistency just says, due to Lamport, says if you have a thread out there which is running instructions or tasks, let's just call them instructions A and B, and another thread which is running in parallel that has C and D, then a bunch of different orderings are OK with respect to the global memory order, right? You're allowed to have AB followed by CD. You're allowed to have A, C, B, D, which is interleaving. Or you can have, as you can see, CD followed by AB. But you cannot have this reversal of ordering of instructions inside of a particular thread, which is that you can't flip A and B, right? So that's sequential consistency for you. The important thing to note in this slide is that there's freedom. Okay, it's not like I asked for a specific global ordering. I said, the global ordering has to be any one of these. And there's obviously like a super exponential number if you have lots of threads and so on, right? So there's some freedom here. And what we'd like to do in our work is exploit this freedom to make things run faster and to avoid dependence, right? So that's it. I mean, you could leave and you would gotten something from the top, okay? I hope you don't. So can we exploit this freedom to avoid dependency? And so I want to tell you in detail about two different projects that Shang Yao led that show you how you could do better with respect to doing cache coherence better in the context of a multi-core processor by using these notions that I've talked about at the high level, but integrating the notion of physical time and logical time. And so I'll tell you about the TARDIS cache coherence protocol. And then together with Andy Pavlo, who's a professor at CMU in the database group, and Daniel Sanchez, who's one of my colleagues, we've done some work on concurrency control, which is a different level of parallelism with respect to databases and concurrent execution of database transactions, where the same ideas apply. And then we got super excited about this over the past few months. And I'll tell you briefly about how this notion can impact things that are pretty basic down at the hardware level. I mean, I think of hardware as basic, just because I grew up in the hardware world, and my thesis is from that world. But atomic instructions, like load reserve and store conditional, there's actually improvements to be had if you think about logical time, even at that level, down at the gate level. And you can certainly go and do concurrency control across nodes in a network. And ultimately, you think about MapReduce and you think about Spark, which came out of Berkeley. You're doing transaction processing at a coarse-grained level. And it'd be wonderful if we could kind of do the same kinds of things. It would require fault tolerance and a set of related ideas. But we think if all goes well, that we could do things like transaction processing of the MapReduce variety at a much more fine-grained level, where the tasks could be small transactions and not have to be 64 megabytes of what have you. Right, so I'm not going to spend much time on that, but as Bjorn mentioned, I'm here for the duration of the semester. I'd be happy to talk to folks about it in depth. So let's start with cache coherence and move on to concurrency control. A little bit of context with respect to the background associated with cache coherence for those of you who've either not done computer architecture or forgotten it. But it's simply a matter of you have lots of copies of the data. Locality is an incredibly important mechanism to achieve computer performance. So you don't want to keep going somewhere far away, to the library to pick up a book. You'd like to have that on your desk, and you'd like to have many copies of the book on different people's desks. And the problem, of course, is that if this book is writable and it's changing, and you need to look at the latest copy, you got a problem here because if you want to change a particular copy of the book, in order to be consistent and in order for correct execution to happen, you have to update all of the copies. And now the game becomes quite annoying. It's really, when do you update the copies? How does this get updated? How many copies are there in the system? And how long do you have to update the copies? Do you need to wait? And it comes down to what your definition of ordering is and what your definition of time is that dictates how you're going to update these copies, right? So if you look at conventional architectures and you look at what's out there, in chips like those in my laptop and GPUs as well, actually not GPUs, but multi-core processors as well, you have essentially a situation where you keep track of all the copies of your data to make sure that you can invalidate those copies when someone wants to write a copy, right? That's it. I mean, it's like a librarian keeping track of all of the copies of the book that he or she has given out. And that implies that when you have a small core system, I mean, relatively speaking, a 64-core system, that's going to take a certain amount of overhead. There's overhead associated with storage. There's overhead associated with telling everybody that they better invalidate their copies and not read them anymore, close the book, and you're going to get a new one, right? But this overhead is associated with storage, the one that's up here on this chart, and it's an order n overhead in terms of every copy of a book. If there are n cores in the system, there's some metadata associated with this that says that you got to be careful about keeping track of everyone who has this, because you better invalidate them. If not, you're going to break your correctness model because some people are going to have inconsistent copies of the data, and they're going to work on stale copies where others will have the new one, and essentially all hell breaks loose. Right? So the way directories solve this problem is through a process of invalidation, where before someone wants to write the data, they broadcast to the order n cores that they know about, or they broadcast to everyone. If you happen to have this, invalidate, don't read it anymore. You're not allowed to read it anymore because I'm going to do a write, and the next time you read it, you're going to have to go get that copy. All right? So that's painful, it's centralized, it takes a long time. And we'd like to completely eliminate that, right? And we will. Yeah, go ahead, Carlo.
What about the question, if there was a read request before the book was updated, and it's kind of making its way to the system, shouldn't that actually get the old data?
Absolutely. That's absolutely correct. So it comes down to you do have a choice, even in a physical time system kind of decides that there's a synchronized clock, if you will, right? And the instant I give you ownership of the data, it essentially says, I'm not going to allow you to write that data until I've told everybody to invalidate, and it's percolated through the system and it comes back. So that was a decision that was made for the correctness for sequential consistency because you were forced to use physical time. But you're talking about exactly the degree of freedom that you could potentially have in terms of saying, well, I mean, that read, I was going to do that read before anyway, right? So let me go ahead and do that read, and I can be before that. But you can't, if you want to satisfy sequential consistency, you can't sort of have your cake and eat it too, okay? In the sense that you can't change your mind about what you just did for every different copy of data, right? So that's something to keep in mind, all right? But great question. So there's another way of doing things which doesn't require this overhead associated with the leases, and that corresponds to what is lease-based coherence. So this is a bit like e-libraries where you've all done this. You got a Kindle book from a library, and then God, it disappeared. Because I can't read it anymore. On that last page, and it disappeared, right? Because they just turned it off on you, right? And so that's lease-based coherence, where Amazon is not keeping track of the fact that I have a copy. There's no order n storage here, right? I mean, the point is there's a synchronized clock, which is kind of the bad part here, right? It's potentially based on my system. A little bit of skew here in the Amazon realm doesn't hurt, but in the context of processors, skew is a problem. But you essentially say, look, I'm going to give you a lease, and you can read as much as you want within that lease. But if that lease expires, you're going to go ahead and you're going to have to renew it, right? Which is the problem. And by golly, if someone wants to write it, then that someone is going to have to wait for all the leases to expire. So the person who had the book for the maximum amount of time and was going to return it on Friday, you're going to have to wait till Friday to write this data, right? Now, if it had been someone had it for Thursday, someone had it for Wednesday, and that was it, then you could write it on Thursday, right? But you only store the maximum value of the lease, and so you avoid the overhead, but you are doing a bunch of waiting here, right? So those are the two classical ways that you can solve this problem. We're going to do this in a different way. We're going to use logical leases. We're going to have many different logical times associated with every different program that is running on different processors. And so the PTS is going to be, there's going to be multiple PTSs, program timestamps. And so the bottom, t equals 0 through 1, think of it as logical time. And we're going to have two things. Just like a lease has a start point and an end point, we're going to have a write timestamp that says, this is when, we're going to have this for data. This is when that data got written. So the last time the data got written is in the write timestamp. And this is when you can read the data until, in terms of logical time. Okay, that is your RTS, right? So for the rest of the talk, all of these things are going to mean the same thing. WTS is when you created this data. If you write it, then you're going to get a new version of the data with the new WTS. And RTS is going to be till when you can read the data. All right. In the logical timestamp setting, we're not going to actually do invalidation. Physical time involves invalidation, but we're going to use logical time, and we're actually not going to invalidate data at all, right? And we're going to avoid this centralized or this broadcast and having this centralized accounting. And so we're going to borrow a concept from the database world where we're going to have versions of the data. Yeah, go ahead.
On the previous slide, what does program timestamp mean?
The program timestamp, you can think of it in two different ways. You can think of it as a thread has a particular time, and it has a logical time associated with it. And that logical time is going to be monotonic for that thread, and that is going to obey the sequential consistency. It's going to make sure that A, B, in my example from before, are executed in the right order, right? It could also be the processor core's timestamp, where you could imagine implementing it like every core has a separate clock, right? So I'm going to give you a nice little example of the cache coherence protocol. I don't have numbers for you. The stuff works pretty well. We managed to write papers on it, which means it had to work, right? But it's all going to be qualitative out here. I'm just going to give you examples. I want you to take away ideas and think that there's some cool stuff going on at MIT. That's it. Okay. So whether it's practical or not, who knows, right? So we're going to have a core which kind of answers your question about PTS. In this case, PTS equals 5. You have a cache in the core. This is about cache coherence. And we have a line that's A. And the first letter there just says it's a shared state or a modified state. And then you got two other numbers there that correspond to the WTS and the RTS. All right, that's basically it. So you have a cache, and you also have a shared last level cache that corresponds to the, you can think of it as main memory if you like. Right? So that's your program timestamp, which is the timestamp of the last memory operation that you did. Okay. And then the write timestamp means that the data was created at WTS, and the read timestamp means that it's valid till then, and you have a lease that looks like that. Right? So I'm going to give you an example that is going to show you all this time-traveling hoopla that made for a cool abstract, but there's some substance there. Okay, so here's what happens. So you have a core, and it's got a PTS of 0. The other core has a PTS of 0. It's got a cache, and you got your A's and B's out there, right? So if you have a two-line memory here, right? It's, a trivial example. It has to fit on a slide, right? So what you're going to see here in terms of animation is physical time, okay? So we're going to have two notions of time here, right? We're going to have logical time, but what you're going to see in the animation is physical time, right? And you're going to, I'm going to give it away. You're going to see each of those instructions happen in 1, 2, 3, 4, 5. That corresponds to physical time, just as you see on there, right? But the actual effect of these transactions, if you go back to the local copy example that I gave you, is going to be that the actual time, the logical time in terms of the data that was read, is not going to be the physical time, okay? So that's a little bit of a preview. So let's go through this. Let's do the store. This is just going through the different things, the caches and so on. Let's do the store, and then what happens is you ask for a store request, and you just go ahead and you modify it. There was no owner for it, so you got that, and you do whatever you want. I haven't shown you the data, but you clearly modified it, so the S turned into an M. Okay, that's it. So we go ahead, and when we actually do the write, our write is going to create a new version of the data. So that's going to make the WTS 1. And because this is owned by us, you can just set the RTS to be something greater than WTS or equal to WTS, and that's 1. Right? It's only relevant when it's shared data as to what the RTS needs to be. So then you want to do a load here, and this is a load B, and it's the same core. So we ask for a load request, and so now you're going to get you ask for an arbitrary lease of 10. Think of that as being a number that really was pulled out of a hat. And you get shared data. The data was written at 0 because it wasn't written. It's only been read. And your timestamp was at 1, so you add 10 to it. And for the next logical times corresponding to the 10 logical times, you get to read that data, right? Which could be forever, by the way. If the time doesn't change, that could be for a long time. It's not 11 clock ticks, all right? Keep that in mind. So then you want to store the data. OK, this is the fun part. So now you have shared data. You have a copy of data corresponding to core 0 that corresponds to B. And core 1 wants to write this data, right? And so we talked a lot about how this happens, and I won't belabor the obvious in the conventional protocols. But what happens here is when you do a store request, this is actually something that's shared. So B is shared. But you go ahead and you instantly return exclusive ownership, all right? And there's no invalidation, right? The copy is over in core 0. The thing that happens is you get B, you see M011, but what you do is you jump ahead in time to 12, right? And you say, I'm going to go ahead and I'm going to assume that my clock is such that it's way beyond the clock corresponding to core 0 when the lease expired at 11. And I'm going to move over, travel to the future, to time 12, and I'm going to go ahead and write this data, all right? And you just go write the data, okay? That's it. It's going to be fine because of the degree of freedom that we have in sequential consistency, as long as we maintain the protocol and run it through to completion. So you go ahead and write the data, and that got written at 12, and you were it was 11, and then you had to increment it and write it at 12. And notice that you have two pieces of data, but they're two different versions of data that coexist in physical time, but are in different logical times, right? And that's why this works. And that's it. I mean, there's actually not that much more to this protocol. I'll just go through a couple of more just to see how the rest of the protocol works. But let's say that you want to do a load request of A. Remember that A has now been modified. It's now owned. But there's exactly one place that A can be because it's owned by someone. So this is not like a broadcast or a multicast or anything. You just ask for the write back request. This is the same as regular protocols. And you downgrade that from M to S. And then the reason that goes to 22 is because this core, which requested the load, has a timestamp of 12. And it wants this, this copy for at least 10 of its logical time. So it wants to go from 12 to 22. And then if this goes to 12 to 22, it's a small optimization to make the RTS 22 for core 0. So don't get too hung up on that. The point is that if I want to get a load here with some reasonable timestamp, I wanted, it was written at time 1 by core 0, which is basically equivalent to the time in core 1 at the beginning. But I want it till time 22 because my PTS is already at 12. It doesn't make sense for me to get it at time 11. I mean, it's already expired, right? So
and who determines that you want it for at least 10 units?
so that's, you can do deep learning if you like on that one, okay? I mean, that's all I know about deep learning, that it can be used for anything, right? But that's what I'm getting here, right, at the last couple of weeks at Berkeley. But sorry. I just used 10. I mean, we just said 10, and you could be smart about it, but it was an arbitrary choice. I think you want to be smart about it, and we have some ideas on that, right?
What determines that? I mean, is what you plan to do with the data, or?
It's probably history. In hardware, Carlo, you learn from the past, right? So typically you have loops, and you go through it, you figure out what works, and then you hope for the best, right? Yeah. So that's essentially it, right? So let me summarize, right? So the last load is, there's nothing going on there. You just load that B anyway. So there's no change. The interesting thing here is that if you look at the timestamps, and I'll make this a little bit clearer, there's an inversion here. I told you that 4 was before 5 in physical time, right? I mean, I told you that up front. But if you look at logical time, what really happened, of course, was that all of core 0 happened at PTS equals 1, right? And some of core 1 happened at 12. So really, the logical time for instruction 5 was before the logical time for 4, which was at time 12, all right? And this is fine because of the sequential consistency degree of freedom that we have. So that's the physical time that you saw. This is the physical plus logical time order. And the reason I'm saying it's physical plus logical time order is because I maintain physical time inside of a core, okay? But if you look at what happens, and this next slide makes it, I think, even slightly clearer, but let me just get to the dependencies in a second. All of this happened at 0, and this happened at 11, or whatever that was. So you have a bunch of dependencies there, and these dependencies are not necessarily hard and fast in terms of having to maintain these dependencies, because you have the degree of freedom with respect to sequential consistency in terms of reordering. So what's happened there is that those dependencies have actually changed. You do have this raw dependency that was maintained. Those are the tough ones to get rid of. But really, the war dependencies have gone away, right? Because I just did that right, before in terms of physical time. So I've kind of eliminated that, right? So that war dependency over here is in a different color, simply because it really it didn't change the latency of my system, didn't change the performance of my system. I did that right when I wanted to. All right, go ahead, Jan.
Is there any chance you ever going to get into Devadas numbers?
No, there's no chance, simply because, and we can prove it. So we do have a proof of that. There's a live lock situation that corresponds to time standing still that I'll get to in just a minute. Okay. Physiological time, hard to say. We called it physiological time. That's my contribution to this work. So you have all of things happening at time 1, and these things happening at time 12. And that's what you see here. And the ones happened at the same logical time, so clearly we had to have them in a particular order. So that's why this is not just logical time, there's physical time as well, because those things had to happen in the physical time order, right? We have to disambiguate that. And so our equation here is pretty straightforward. You're allowed to have timestamps, unlike Lamport clocks, you're allowed to have timestamps that are exactly the same, right? So all of us could have the same timestamps. If we're all sitting in the same core, physical time would determine what our order was, right? But if we're in different cores, then you'd have to have different timestamps, or you can't make any requirements on the ordering of things that have the same timestamp outside of the same core. But within a core, you can use the physical time to disambiguate two logical two transactions that happened at the same logical time, right? So that's our definition. And we can prove that TARDIS obeys sequential consistency. Go ahead.
What does it mean when the subscript is attached to an operator like equals or less than?
Oh, so this just means what is the equality defined in terms of, right? So when you have equal L, this means that the logical times associated with this equality are the same, and here the physical times associated with this equality are what's attached to that, because they have two different notions of equality here. Right? You have the logical time equality, and you have the physical time equality or inequality. So I have to disambiguate that if I want to, put something up here and make it look cool, right? So, so that's basically it. So that's TARDIS. In a nutshell, I'm going to tell you about what it does and what its problems are. Right? What it does is at this point, I'm kind of done talking about it. There's scalability because there's no multicast, there's no broadcast. Okay, I never have to tell all of you to do something. Okay, it's always one-on-one, right? And there's no storage. There's some issues. I have to renew the leases. Carlo asked a great question. How did I decide the 10? Right? And if I can't use deep learning here, I got to do something different. I have to renew the leases. I have to pick the 10. And the nice thing here is that you end up being able to hide this using notions that are fairly fundamental to computer architecture, which simply says that, look, the reason I had a lease renew maybe was because I jumped ahead in time. So all of this data that I have became stale. It expired because the RTSs of that data are less than my PTS. Right? This happened instantaneously, which is bad, right? But what that means is that that data hasn't actually changed because this happened instantaneously. So I could speculate that this data hasn't changed and just go ahead and do your usual, most the processors, the high-end processors are speculative. And I just speculate that this data hasn't changed and ask for a renew. And if the renew comes back, I'm good, no overhead. If it doesn't come back in 1%, whatever percent of the cases, I'll have to recover from that, right? So you hide the overhead of lease renew through speculation. Timestamp sizes, if you had 64 bits, they would never roll over, right? But it turns out you can make them 16 bits. If you wanted, you can make them 8 bits because you only need a limited amount of history, right? So there's a bit of detail there. And you can do compression for that. There's a problem associated with time standing still because reads don't increment, right? This is actually a good thing because you can keep the data, and as long as you're local, your time doesn't change and your data doesn't expire, right? So this is actually good in a way. But if you were doing spinning, if you did horrible things like writing spin locks, which you're not supposed to do, by the way, in modern systems, but if you did that and you had legacy code, you actually have a live lock problem. The easy way of getting around that is to increment time a little bit every once in a while. The more interesting way is to actually detect spinning and take care of that and actually keep the time as slowly changing as possible. One of the nice things that came out of this, and I might have a slide on this, is that the amount of parallelism that we can discover in a system is related to the rate at which the timestamps grow. So as timestamps stay static, it means that we're just performing local computation and everybody's running in parallel, all right? So this is actually a good thing. Time standing still is a good thing. You can get more done, okay? Homework, you can get more homework done, right? So that was TARDIS. I have a few minutes. Let me talk about this other work that is quite related and doesn't require as much context, but it's quite different. And I wanted to talk about this because I didn't want you to go away from here thinking this was a hardware talk, right? There's more here in terms of the notions. So in concurrency control, which is in the database world, you have a different correctness criterion, which simply corresponds to I have these transactions. They could be run in parallel. And as long as they're atomic, I'm cool. Okay? I just can't, I can order them any which way, but I can't have that. Right? I'm sorry about the font. It says I can't have this. So you can't have things stepping on each other. Okay? Because you can see from there that the read and the write kind of stepped over each other, and you violated atomicity. Okay? So that's the concurrency control world. And it's kind of the same thing. People solve this using centralized time allocation. You can do it with timestamp ordering, which is you have a central timestamp allocator, and the timestamp allocator or you could do it with two-phase locking. There's scalability issues associated with that. You assume a synchronized clock. Again, similar things in the cache coherence world. And there's you could get aborts because of clock skew. So things don't scale beyond 100 cores. The one thing that happens here is that in the logical world is like I said before, Bjorn got a timestamp, Carlo got a timestamp, I got a timestamp, and then we went off our merry way and did whatever we had to do. The point is that in the database world, prior to the TikTok work, timestamps were allocated before you executed the transaction. So you asked a timestamp allocator for a timestamp, and you got a number. And that causes a problem, simply because you can, in some cases, the timestamp order works. In other cases, you have to abort, right? I'll give you a simple example of that, right? In this case, what's happened here is that the top one got timestamp 1. Transaction 1 got timestamp 1. Transaction 2 got timestamp 2. And when this happens, everything is good, right? The read is supposed to get the old value because it's the TS1. The write, as you can see in physical time, happened after the read. So you're good. You got the read properly. So this is going to work. But if you did it the other way, and this transaction had timestamp 1 and that transaction had timestamp 2, current concurrency control algorithms will abort this transaction because this one is already committed with timestamp 2, and this write, this read happened should happen after the write, but it actually happened before the write, right? So that read should have seen the value of the write because of that arbitrary order that we imposed on the first one having timestamp 2, right? So it's a bit of a problem, right? So you'd like to minimize aborts, and you can do this using similar ideas to what I've talked about. And you can, in the traditional sense, you acquire a timestamp and determine whether you can commit or not, traditional. In the TikTok's world, we're going to do what we did for cache coherence. We're actually going to remember the WTS and the RTS for each of the read tuples and the write tuples that we have. Each of these things are addresses. They're exactly the same as the cache coherence world. We're going to remember all the tuples that we read and wrote. There's going to be 5 of them, some small number. We're going to remember that, and we're going to compute a commit timestamp based on, after the fact, in a lazy way, to obey our correctness criteria. And because we do this in a lazy way, in that previous example that we have, we'll never abort, right? Because we'll get to the end, and we'll choose the right timestamp for the transaction in all cases, regardless of what order they happened in, right? So that's kind of the gist of the idea. Right, so let me give you a little more details and end here. We got about maybe 5 minutes, and then, so maybe a little bit longer, 7. How about 7? Sorry? Logical or physical, thanks, that's right, yeah. Right. Yeah, right, time stands still. Okay, let's pretend, the clock stopped, right, for the next 5 minutes, okay? So in TikTok, I have a little example here, which is very similar to the cache coherence example that should kind of put everything together. So I think this is a nice one to go through. So you have a read phase, you have a validation phase, and you have a write phase. The read phase is when you kind of do your work, right? You go do your reads. You're also, interestingly enough, in the read phase, you're actually doing local writes as well, okay? And the validation phase is when you commit you create your timestamp, and it's exactly the same tuple format. So we're going to read and write tuples, even though that's called the read phase, but the writes are local, okay? And you're going to execute the transaction. In the validation phase, we're going to actually compute the commit timestamp. In some cases, we'll have to abort even in our algorithm, but in many cases, like the one I showed you, you will find the right timestamps. And then finally, we're going to update the database after we've computed the commit transactions, right? So in terms of a picture, here's a little picture exactly like the one I showed you before in a conceptual sense. What you see up there are the database states, and what you see down below are the local states corresponding to each transaction that may be running on different cores, right? So you have tuple A and you have tuple B. Those are the WTSs and the RTSs. Everything is logical time. So load A you're going to just load a snapshot of tuple A, the data, the WTS, and the RTS. Nothing here, right? Load A for transaction 2, same thing, right? Store B, well, what happens when you store is you have to store B to a local write set, which means that you have to create a new version of the data, which essentially means that you have to basically, the local write set, store B simply says you have to stretch this because you have to create a new version of the data. So your RTS has to be incremented to that value. And then you load a snapshot of tuple B as well, right? So that's the same as before, nothing different. Now we're going to compute the commit timestamp. This is really the key. So what does it mean to compute a correct commit timestamp? To compute a correct timestamp, what you need is all the data that you've read has to be valid. It has to be between your WTS and your RTS. And obviously, if you're writing data, you have to be allowed to make a new version of the data, right? So if you look at the equations that we want, the read set says that the commit timestamp has to be chosen such that it's in between WTS and RTS, like I just said. And with respect to the write set, we want the commit timestamp to be greater than the tuple RTS plus 1, because someone else may have this tuple with this particular RTS, and we want to create a new version after all of those versions have expired, just like in the cache coherence protocol, right? So if I want to write something, I need to write it after it expired, right? Because I want to create a new version. If I want to read something, I want to read it within its lease, right? So if you do that, then you want to compute, that is your commit timestamp for the transaction 1. And as you notice, we need an RTS extension. Let me just go back here. This is not true for this value because I need this to be after, and the RTS expired right there. So I'll have to ask for an RTS extension if I want this commit timestamp to be that. If I don't get it, I have to abort. And so that's my commit timestamp. It commits at TS equals 2. And at that point, I can go ahead and write it to the database because I've computed a commit timestamp. Now I'm going to go ahead and try and compute a commit timestamp for transaction 2. There's only reads in transaction 2. It's a little bit easier. And so I can go ahead and choose the commit timestamp to be in between these valid values, which is just 0 over here, right? Because it was only reads for that, right? And so what has happened here again is I've committed transaction 2 that happened later in physical time at an earlier logical time that correspond to timestamp 0, right? Because that's T2 commits to timestamps equals 0, but T1, as in the animation, happened earlier in physical time at timestamp 2. So similar notion of time travel that we had with respect to the cache coherence protocol, right? So that's about it. You can prove that this local decision gives you a global correctness property of serializability. And it's not this is actually a simpler proof than the cache coherence protocol. Transactions may have the same commit timestamp. And this is actually real numbers. If you run a benchmark with different contention rates, more contention means less parallelism. You see the logical timestamps growing faster. Right? So that gives you a sense of how fast you can run, how much parallelism you have in your application. So that's pretty much it. That was the meat of what I wanted to get across. Very briefly, I want to tell you about all the things that I guess will happen when I'm away, perhaps more efficiently, which is we want to work on taking things like the RISC-V, which is a great processor that came out of Berkeley, and doing a few things to it with respect to the synchronization instructions. There's a problem of live lock. Those of you who have done computer architecture know that when you do load reserve and store conditional, there's an annoying problem of live lock that is associated with what's called the ABA problem. If you try and fix the ABA problem, you get live lock. And it turns out if you use WTS, you can kind of elegantly solve the problem. And we're changing the RISC-V microarchitecture to do that. It doesn't change things from a practical standpoint. I'll be upfront with you, but it's just kind of nice to be able to say there's no live lock. You know, there's a proof associated with that. I talked about cache coherence. We've taken the consistency models that are used in the world are the x86 consistency model, which corresponds to total store order. And so I just showed you what happens with sequential consistency. You get more relaxation, but our protocol does change. We'd like to build something that we're calling the T1000. We're kind of into time travel, the only good Terminator movie. And we'd like to build across multiple FPGAs because we think our cache coherence protocol is more scalable than others. We'd like to show that it is by running it on a heterogeneous network, which doesn't have a lot of bandwidth. Inside of a chip, you have lots of bandwidth, but when you go off chip, you have less bandwidth. So that's the reason for that. I talked about concurrency control and told you about the ideas. We'd like to essentially take this and move to the multiple node data center world, where currently databases don't actually do local caching of remote data, but now we have this nice cache coherence protocol and these ideas. We think we can do local caching of across nodes and databases, nodes meaning computer nodes in the database world. So that's ongoing. And ideally, we'd like to do fault tolerance and a bunch of other things. And so let me leave you with the real title of this talk that I was afraid to put on the internet. But here you go. Thanks for your attention. And thanks for the questions.
We have a couple minutes for questions, so just raise your hand. I'll bring the mic to you.
Thanks for your talk. It was really interesting. I wonder if you could motivate a little bit why you're pursuing cache coherency for these many core systems as opposed to just explicit data movement.
Right. So that's a great question. There's a couple of different ways of answering that. Kind of the glib version of the answer that I have is shared memory systems are most people would agree are easier to program, and you have if you could get the same overhead and the same performance out of a shared memory system that you could get out of a message passing system, then people would build a shared memory across these different nodes. And so now we haven't actually proven that. And the reason that's a little glib is because we haven't actually shown that. And part of what we want to do with building this large processor is actually to show that, right? And so you can imagine that now nobody's going to use that T1000 thing, right? I mean, it's FPGAs. It's going to be clunky, but it may be a simulation framework for simulating architectures and doing things like that. And there are people out there like my colleague Joel Emmer who are in an FPGA domain within a single FPGA. He's building infrastructure to provide a shared memory abstraction for doing architectural simulation because he believes that is an easier way to sell architectural exploration using emulation to computer architects who don't necessarily write highfalutin object-oriented programs, but they still like shared memory, right? So that's the main reason. I will say, I mean, usually it's like you have an idea and you kind of try and find a problem that the idea is applicable to. So this is a little bit of that, right? But I do agree with you. It's not kind of an obvious sell that shared memory is going to be the wave of the future. Right? So, yep.
I have another question. So you said you're not going to show us numbers and stay on the conceptual level, but do you have speculation about what type of workloads will really amplify, where the benefit of these techniques will be most, especially visible compared
I mean, it's
to
not
other
speculation
workloads
because,
where it'll be a wash?
Yeah, I mean, as I mentioned, we had to get the numbers. It's too bad that these days, you can't just have a nice idea and get a paper out of it. Back in my time when I was your age, you could actually do that, right? Tough break. You guys, were born too late. But so we do have numbers. So it turns out that that it's the storage in the TARDIS protocol. It's really the storage overhead as you get to 256 cores and beyond that improve. So we match the performance. It maybe gets a little bit better, right? So there's no reduction in performance. Part of the reason why we'd like to move to other domains is that inside of a computer system, or inside of a chip, I should say, latency and bandwidth they're actually not that bad, honestly, right? I mean, things are pretty fast inside a chip, okay? And so when things are pretty fast inside a chip, this notion that you're waiting for acknowledgments and so on and so forth doesn't actually hurt you that much, right? So we were happy to meet the performance and the energy and the network traffic and perhaps improve them slightly on kind of the usual benchmarks that we need to run. And we could show a storage overhead reduction. And on top of that, I think the protocol is a little simpler to build if you're a hardware architect, because the number of states that you need in a cache coherence protocol. So when we did some of our verification work, in terms of showing this and trying to prove it, the number of states in a regular cache coherence protocol is larger, than the number of states that you need in the TARDIS protocol, because we don't have to send everything out and wait for acknowledgments and worry about all these cases where things break, right? So that's one side of it. The concurrency control is actually maybe an easier sell. I mean, it's software. It's out there. It's downloadable. You could imagine taking that and plugging it into a database system. And we saw a factor 2 improvement in throughput and a substantial reduction in the aborts, especially when you had high contention workloads, right? So.
All right, if there are no more questions, then let's thank our speaker.
Thanks.